Hello everyone, welcome back. Today we will solve problem 22 in DeepML, which is called Sigmoid activation function understanding. Now in this problem, we're just going to write a Python function that implements the Sigmoid activation function, and it's very straightforward in terms of code. It can be done in just one line. But to make this video useful, what I'm going to do is I'm going to talk about the Sigmoid activation function, why it is relevant, why do we care, when do we use it, and what it is exactly. So without any further ado, let's dive into it. So you may have seen the Sigmoid activation function referred to some places. Usually it's denoted with this as a sigma, and it's defined as 1 over 1 plus e to the minus x. This is the exponential function. And you will also see it written down like this. And there's an important difference of how you write it, depending on what you want to do. And I'm going to talk a little bit about it briefly. So to understand why this function is used or why it's relevant, it's important to see the graph of the function itself. So if these were the y and x axis, then this green line represents the sigmoid function. And it's going to have this kind of S shape like this, 0.5. So this function is used in binary classification tasks mostly as part of the activation function. That is, you work through your neural network, you have all your weights, your biases, you fine tune all of that good stuff. And then eventually when you get to the end of the model and you want to figure out if your input belongs to one class or not, you would have this function which makes a decision. So this may not be the most efficient way of doing it, but for example, if you had an image of, if you wanted to buy a classifier to see if an image that you're giving it is of a human, then the output of this thing given an image would be the probability that the image that you gave it is of a human or not. And so this is why, this is kind of a neat explanation of why they utilize the sigmoid function for this kind of thing. Because if you look here, you cross the y-axis at 0.5. So that means that if the input that you give the sigmoid function is something positive, then what that means is that your output is going to be a positive. It's going to be a positive number. So it's going to be something greater than 0.5. And if you give it something negative, you can decide where to put the 0 in this thing. It could be less strictly or less or equal. It doesn't matter. Then you're going to get something that's lower than 0.5. And so if you think about it, if you're trying to make a decision about something that's binary, for example, a coin flip, then the probability of having one output or the other, it's 0.5. So what the interpretation that you get when you use this function is that, let's say you get a positive input and your output from the sigmoid function is 0.7, you can interpret that as saying, hey, this image that you gave me, this input that you gave me, has a probability of 0.7 of being of the positive class. And the positive class is just a fancy way of saying whatever class we decided is going to be represented by 1 or 0. So this is why we utilize the sigmoid function, and that is its main use of the binary classification case. Now, as I said before, if you want to implement this on Python, it may seem already, if you have some experience with it, it may seem very straightforward. Now, we would have to think a little bit about which way we want to write this down here. So as I said before, we had these two ways of writing it. But the one that's mostly preferred in practice is this version right here. The reason is, if we think about it, we can have an x that is an input that's very, very large, right? X very, very large. This is a way of saying that is super, super big, super, super big compared to 0. So if we were to have that, then if we have to calculate this part right here, exponential, we're going to have potentially a number overflow, because this thing is going to be such a big number that the exponential of a big number becomes an even bigger number. And so this thing is not as practical. Whereas here, if we take the exponential of the negative of a very big number, the only thing that's going to happen is that this thing could saturate and go to 0, because the exponential of a very negative number gets closer and closer to 0. So this is why this implementation is preferred, and this is the implementation that we're going to go with. Now, before I write the code, let me tell you a bit more about the sigmoid function that could be helpful when you're studying or when you're trying to get familiar with how it is that you're going to do this. If not, this is entirely optional. It can help you enhance your knowledge, but if you're only interested in the code, you can just jump to the timestamp of the solution. So one thing that you're going to hear mentioned a lot is that people are going to talk about the linear boundary property of the Sigmoid function. And the only thing that that means, and it's somewhat confusing in my opinion, is that the Sigmoid function can split space between two cases, as I said before. So if your input is something negative, something over here, then all of the elements that you're going to, sorry, this line should have been vertical. I apologize. So what you're saying here is that any input that you give it that's negative, right, to the left of this light blue line, which should be the y-axis, all of this is going to be classified as 0. And all of the things that are to the right of it are going to be classified as 1. So the good thing about that is that it's somewhat intuitive, right? You don't have a funny shape. Like, for example, you could have a classifier that has a boundary like this, maybe. This would not be a very good classifier, but no, that's not a function. You could have a very wonky shape, something like this, right? Let's suppose that this thing doesn't overlap, but you could have a very wonky shape like that. So if you had that very wonky shape, then it's not as straightforward to say which class an observation is going to belong to. You cannot tell much about it because it's just weird, right? It's not as straightforward because depending on your X value, you also have to look at your Y value, because for this same X value, for example, you could be below this line, which means that you're from one class, or you could be above this line, which means you're from another class. And this behavior is not very straightforward. Whereas here it's very simple for the Sigmoid function. It's either to the left or to the right. That's it. So that's what people say, what people refer to when they talk about the linear boundary and why it's relevant. The other important thing to know about the Sigmoid function, and you can verify this yourself, I'm not going to do it for the interest of time, is that if you take the derivative of the Sigmoid function, you're going to find that it's just going to simply be expressed in terms of the Sigmoid function itself. It's going to be the sigmoid times 1 minus the sigmoid. Why do we care about the derivative? Well, when you're doing backpropagation on a neural network, you care about the derivative of your activation function. And ideally, you would like to have an activation function that has a somewhat neat derivative. And by that, I mean that's easy to calculate. And the sigmoid function is amazing because if you know the value of the sigmoid, you get the value of the derivative for free. So that's also another reason why this function is so important and why it's so widely used. And finally, the last thing, and this is just for some fun piece of trivia that you can impress your friends with. Although in machine learning we call this thing the sigmoid function is actually a family of functions. Within that family of functions, there's the logistic functions, which is another family. And what we call the sigmoid function is commonly known as the standard logistic functions. So this is just a complete misnomer. We should not call, well, in theory, we should not call this thing the sigmoid function because that's incorrect. It's a family of functions. But in practice, nobody will care. If you tell them sigmoid function, they will think you're talking about this. I assure you, pretty much nobody ever has thought about, well, some people have, but most people don't think about the whole implication of the family of functions and all that. I'm just telling you to enhance your knowledge because knowledge is beautiful and to try and impress somebody if you're losing an argument and you need something to make yourself feel more important. Okay, now that we talked about the sigmoid function, let's go write the code. We're going to do something very cool, and we're going to do a one-liner. So we should return the output rounded to 4 decimal places. So we're going to use the round function for that. And we're going to pass as a second argument 4, which is the decimal places. Now let's write the sigmoid function. And as I said, we're going to prefer the first form I taught you about, which is 1/1 plus the exponential. How do we write the exponential Python? There's multiple ways, but because we are using the math library, we're going to do math.exp. And then the argument that we want to take the exponential of is c. So we're going to do minus c in the argument. And with all of that, we are good to go. I prefer this specification because the other one could generate out overflow, as I already mentioned in the video. And with that, we pass all of the test cases in the hidden one, and that's it. So again, it's very, very straightforward code. You can do it in one line, but what's important about this is to understand what the Sigmoid function is, why do we care, and when do we use it. I hope that this video helped you understand more about the function, and if you have any other questions, feel free to post any comment, and I'll try to get back into it as soon as I can. Thank you so much, and happy coding.